So let me do an example for you. Let me go back to example 16.1. Let's use the same curve C, which is the unit circle centered at the origin, and traced out once counterclockwise. So we are going to once again evaluate a vector line integral, but this time we're going to evaluate the flux across C. And we're going to do it for the same two vector fields that we did in that example. So I say then compare your results to example 16.1 and interpret them in terms of circulation and flux. So let me remind you what we already did in example 16.1. So for this vector field here, we had calculated that what at the time we called effectively work, or the vector line integral, was equal to 2 pi. So we now have a new interpretation for this, and this is the circulation. So the fact that the circulation now is positive for this vector field tells us that if I draw this curve C, which is the unit circle centered at the origin, this vector field F, which is this one over here, is pushing this bead around this unit circle wire in the same direction, in this case counterclockwise, that the curve is traced out. So if I scroll down and remind you, here's the plot of that vector field. Again, we draw our unit circle here, traced out counterclockwise as I just did. You can see, of course, that if I put a little bead here, this bead is going to be pushed around because all of these vectors are pointing in the counterclockwise direction. It's going to be pushed around in this counterclockwise direction. And if I wait until it's pushed around exactly once, so it sweeps out the curve once, then the circulation is 2 pi units. And again, we won't talk about the units here because we have no information about units for the vector field F or any of the X or Y measurements. Okay, but in other words, we have positive circulation. The vector field moves the bead in the same direction that the curve is traced out. Okay, so how about over here? So we had talked in that example about the fact that when we did this second vector field over here, this one, 2x, 2y, which is a conservative vector field. In fact, both of these, I believe, are conservative. But anyway, don't quote me on that. We would have to check that. This vector field is definitely conservative, and we had calculated its line integral to be 0. So if we go back and look at its vector field, if I draw the same unit circle, and use the same color as before, we notice that the vector field, because it's orthogonal everywhere to this unit circle, makes sense because the unit circle is one of the level curves of the potential function of this vector field. And we know gradients, which is the vector field, are orthogonal to these level curves. So anyway, because the vector field is orthogonal to these to this curve, then the vector line integral from module 1, that work integral, which we now know as circulation, it makes sense now that it's 0. Because if I put my bead here, there is no movement that the vector field generates that goes along the curve. The bead would just stay there. It feels like it wants to be pushed out away from the origin. If I freed it from this blue unit circle curve, so already we have a sense that if we calculate the flux of this vector field through this same curve, we're going to get a positive number. Because, again, if we removed the actual wire, the curve C here, but we kept the bead, the fact that the vector field pushes everything out, we would see some movement, and we'd see movement of this bead away from the origin. So we already have a sense that for this vector field, this red one up here, we're going to get a positive flux, but we'll calculate that in a minute. Same thing over here. If I start talking now about flux, this vector field on the left here is effectively everywhere tangent to the curve C that we were looking at. So, it has no normal component. So this bead is just being, moved and rotated around the circle, but it's not feeling at any point along the circle any push in the normal direction because the vector field vectors are already tangent to this circle. So we expect, in this case, to get a 0 flux. We expect that if we were to remove this fictitious wire of a circle and just let the bead roam free, it would still rotate, but it would not fly out or fly in. No net flux, so we would assume, or we would expect, that the flux would be 0. So given all that, let's go off and actually calculate the flux for these two vector fields. So I'm going to start by writing down our expression for the flux. That's f dot n ds. And then writing out what this translates into based off the work we just did. So for the vector field over here, I have minus y and x. And then over here, remember this, if I scroll back up from the work that we did, is this quantity. So I'm actually going to write this out instead. It's a little cleaner. So we're going to say f dy minus g dx. Okay, and I know that the f in this case is negative y. Negative y. Oops, I don't know what happened there, but I will try to get back to where we were, more or less. Oops. Okay, so it seems to have erased a lot of what I did, but that's okay. Okay, so we'll start all over again. So we were calculating negative y dx, negative y dy, so that is f dy, and then minus g dx. So the g here is just the vector field x, so that's x dx. Okay, and we had parametrized this as a circle, and remember that in that parameterization, x was equal to cosine of t, so maybe I'll write it down here somewhere. X was cosine of t, unit circle. Y was sine of t. And we had our derivatives, negative sine t and cosine of t. So now we're just going to substitute everything into here. So we get negative y, that's negative sine t, times dy, that is cosine of t. Cosine of t. And there's going to be a dt here that's going to be common to both terms. And then we do minus x, which is cosine of t, and then dx, which is negative sine of t. Great. And my integral here is going through from 0 to 2 pi. We're sweeping out the circle once. So now let's see what I have in the middle here. So I have minus cosine times sine plus cosine times sine. So those cancel out. So I get 0 for my integral. And this is, again, what we expected to get. This is the flux of this vector field, which is a rotational vector field, that one. This is the flux of this vector field across this curve C. And again, we can see that because it makes sense because the vector field vectors are tangent to the curve C. So there's no movement orthogonal at any point along the curve generated by this vector field. Okay, so we have a 0 flux there. So now let's go off and calculate the flux as the second example for this other vector field. So a similar thing, I'm calculating f dy minus g dx. And in this case, the vector field is different. So f is 2x dy minus, and then g is 2y dx. And then I go back and I use my same 0 to 2 pi in dt, but now I'm jumbling the integrand in a different way. So I'm going to pull out the 2 here because it's common to each one of these, and then I have x times dy, so x was cosine t, and then dy, looking down here, was cosine t also, cosine t, minus y was equal to sine t, and then dx we get from over here, which is negative sine t. All right, so this time around I have cosine squared plus sine squared, so that's equal to 1. And this integrates to 2 pi, so I get 4 pi. So as expected for this other vector field, I have a non-zero flux. Moreover, I have a positive flux. So this tells me, if we go back to our interpretations here, that the vector field f is acting as a source because the flux through C is positive. So a positive flux means that there's more fluid passing through C in the normal direction than in its opposite direction. So if I go through here and illustrate that, I'm going to draw, oops, let me use this marker, this pencil. I'm going to draw the unit circle. That's the curve C. And, I'm going to draw the normal vector at these points. And you can see why things have ended up being how they've ended up being, because the vector field points exactly in the direction of the normal vector at every point on this curve. All of the red arrows point in the direction of all the green arrows. So if you think about this curve C as being this kind of fictitious circle or this kind of hula hoop analogy, and you think of the vector field as being the velocity field of water in a stream, then it is rushing by this curve C at in exactly the same direction at all points. It's going out of the curve C. So there is fluid moving through the curve C, and it's all moving in the same direction, moving outward. So all of those F dot N contributions that are the integrands of our flux, these are all positive. The vector field F and the normal vector are all in the same direction. And then we're adding them up along S, so we get a positive number, specifically for pi for this example.